Hello everyone and welcome back to my channel. My name is Dr. Onyebuchi Joseph Wandiogbu, and today we will discuss UV visible spectrophotometer, principle, operation and application. If you are a student, a lab analyst, a researcher, it will be good that you lend me your ears and watch this video to the end. Don't forget to like, comment your questions and share our videos. In order for us to start, because anytime you operate a spectrophotometer, you will have to allow it to warm up for at least 30 minutes. So therefore, I want to turn the UV visible spectrophotometer on. As you can see, it is on now. So the next is that we'll continue with our discussion. Now, UV visible spectrophotometer finds application in water analysis. It can be used in determination of inorganic anions like nitrates, like nitrites, like phosphates, and so many others. You can as well find analysis in the textile industry, where it can be used to analyze dyes. It can be used in the pharmaceutical industry, in the food industry, and as many industries that it finds applications in. First of all, UV visible spectrophotometry lies in the absorption of UV visible light from the electromagnetic spectrum. In terms of UV visible, if a UV visible light passes through a substance or a solution, some of the lights will be absorbed and some will be transmitted. Now, the amount of light that is absorbed, if properly measured, relates to the concentration of whatever that is present in the solution. This particular phenomenon relies on the dear Lambert's law that states that absorbance is proportional to concentration. Mathematically, what it means is that absorbance A is equal to EBC, where E is the molar absorptivity, and the B is the path length, and C is the concentration. And from what we said earlier, that absorbance is directly proportional to the concentration, what it means is that as absorbance is increasing, concentration as well will be increasing. In this UV visible spectrophotometer, there are basic components of it. The first of the components is the light source. Apart from the light source, you have the monochromator. The monochromator is what separates the light. And then we have the sample compartment. This sample compartment, this is where you place the cuvettes. If we see, this is cuvette, this is a glass cuvette. In the UV visible spectrophotometer, there are two different types of cuvettes that is being used, the glass cuvette and the quartz cuvette. The glass cuvette is used in the visible region, whereas the quartz cuvette is used in the UV region. The UV region does not use a glass cuvette because glass absorbs in that particular region of the spectrum. Now, as well, we have the detector section and we have the readout. Now, for us to be able to understand how to use a UV visible spectrophotometer, the first thing we have to do is to on the machine, which we have already done prior to starting whatever we are doing, so that it will give it time to preheat. Then the next is for us to have our standards, because for every determination you do in UV visible spectrum, in short, anything you are doing in a spectrophotometer, you have to do what is called calibration. So these are standard solutions that we use in the calibration. And for today's video, we are using a methylene blue to depict our experiment today. So these are different concentrations: 5 parts per million, 10, 15, 20, 25 parts per million. As you can see, the concentration is increasing gradually. So what we'll do is to feed these concentrations to the UV visible spectrophotometer and obtain their absorbances. Then we can be able from that to make a plot of absorbance versus concentration. Now, in order that we start, the first thing that we'll do is to zero the machine. That is bringing the machine to zero. So we have to first of all bring out one of the cuvettes and then rinse it with water. This is distilled water. Then we add water, distilled water, and then we clean the walls so that it will be free from water and some other things. Then we place it in the sample holder and then bring it to zero. As we've brought it to zero, the first thing we have to do, the next thing we'll do is to search through the wavelengths so that we can get the best wavelengths where we will perform this analysis. So I clean another cuvette. And then place the sample. Still zero the so as you can see, this is in absorbance. So and we've brought the machine to zero. The next thing we'll do is to start changing the wavelengths. So at 400 nanometers, we got the absorbance to be 0.95. Then we change to at 410, we got it 0.019. 420, so as we get to 500, we bring the machine to zero using the distilled water, and then we take a reading of the sample. Then we are just scanning through the wavelengths to get the wavelength where the machine will show the maximum absorption. This is 600 nanometers. We got an absorbance of 0.369. move to 620 nanometers. And we take our reading. At 620 nanometers, we get 0.492. And we move to 640. 640 nanometers. And we get the absorbance to be 0.588. Then we shift to 660. Get it to be 0.885. 680. Zero point 994. So at 700, we can see it is now dropping back to 0.130. So from our examinations, you can see the different wavelengths and the absorbances that we got. From this, we can see that 680 nanometers gave the highest absorbance. So we will have to set our wavelength at 680 and perform the test. Now, in order that before we perform the test, we have to now measure the absorbances of our different standards. So already I've added the first standard here, which is 5 ppm. Then we measure the absorbance of 5 ppm. We got it to be 0.718. Then the next we'll measure will be 10 ppm. So I have to remove the 5 ppm. And then rinse the cuvette with distilled water. Then we add the 10 ppm. Once we add it, we ensure that we clear the glass part, the part that the light will pass through. Remember that the wavelength that we are working is 680 nanometers. So you can see the machine is at 0. Then we take the reading of the absorbance. And the absorbance is 1.419. Then the next will be to run the 15. We clean the Okay, so we take the absorbance of 15 parts per million, and they give us 1.724. Then the next will be to add 20 parts per million. Still remember that you have to clear the light parts, make it free. So as you can see, the machine is at 0. So once we change the cuvette to where the sample is, at 20 ppm, we got it to be 1.964. Now we take the last of the readings. At least anytime you are performing calibration, it is important that we use at least 5 points, at least 5 different standards that will be increasing in concentration. So we take the last, which is 25 milligram of parts per million. You can see the machine is still at 0. Then we draw the cuvette holding the sample. And at 25 ppm, we got the absorbance to be 2.198. Now, in order to make our plots of our calibration, what we'll do is to key in our details. You can see the results. At 5 ppm, the absorbance is 0.718. At 10 ppm, 1.419, and then as it increases. So we make a plot of the Lambert law, which will give us, from the plots, this is the concentrations: 5, 10, 15, 20, 25. And we'll have our absorbance 0.718, then 1.419, then 1.724, and 1.964, then lastly 2.198. Now I'm making this plot with Excel. I go to Inserts, click on the scatter. And then for us to get the regression of the equation to see, we click on Add Trend Line, Display Equation, and then Display R squared. Now this is our plots. If we look at our plots, you can see that the regression here is not so good. It's 0.933, but it's greater than, it's over 0.9. Then the equation on the graph is y is equal to 0.070x plus 0.553. R squared is 0.933. Now, what we'll do is to make x the subject of formula. Since y on this plot, this equation of the plot is absorbance. So we make x the subject of formula because x is what? Concentration. Thereby, if we do it, x will be equal to what? Y minus 0.553 all over 0.070. So now, anytime we analyze any sample, whatever we get the absorbance, we put it in this place, and then we derive the concentration. Now, this is a sample of a dye. So what we'll do is to measure the absorbance of the sample. So you can see that I'm trying to add the sample. As I add it, I still clean the light parts. And then put it in this sample holder. Now you can see that the machine is still set at 0. Then we draw the cuvette to where the sample is. And then the absorbance of this sample is 1.320. Now, if we impute this in our equation, that x is equal to y minus 0.553 all over 0.070. That means x is equal to, our y is 1.320 minus 0.553 all over 0.070. If we perform that, we'll do 1.320 minus 0.553. That will be equal to 0.767 all over 0.070. And this divided by 0.070. Then we get the concentration of the sample to be 10.957 parts per million. So with this, we've been able to show how you can use a UV visible spectrophotometer to determine the concentration of a sample. Now, this UV visible spectrophotometer finds application in water analysis. As I've said earlier, it can be used to determine the concentration of nitrates, concentration of nitrites, concentration of phosphates. But bear it in mind that at all times, before you work with UV visible spectrophotometer, you must have to prepare standard solutions of known concentrations, which you use to standardize or calibrate the equipment. If you have enjoyed our video today, it will be good that you like our video, drop your questions in the comment section, and share this video. Thank you so much.